Good morning, all of you. In the last class, we have discussed about the various factors affecting quantity of sewage and stormwater. And today, we are going to discuss about the next topic, that is design of shivers. In sanitary engineering, the design of shiver is very important because the success of any sewerage system depends on it. After estimation of the quantity of sewage and stormwater, the diameter of the shiver is designed properly. And during design of shiver, the minimum and maximum velocity of flow of sewage should be considered, and it should be maintained by providing suitable gradient so that the conditions of non-silting and non-scouring may be achieved. So let us discuss about the minimum and maximum velocity of flow. So generally the sewage contains suspended particles, and these particles when the minimum velocity should be such that the silting of these particles in shiver may not occur. So the minimum velocity is known as self-cleansing velocity, and this velocity can be achieved by providing suitable gradient in the shiver. Generally, the self-cleansing velocity varies from 70 to 100 centimeter per second. Then, the maximum velocity. So, the suspended particles which are present in the sewage may impart scouring action to the inner surface of the shiver, or they may damage the sewer section. So maximum velocity should be such that no scouring action may take place. Therefore, this maximum velocity is also known as non-scouring velocity. So this is minimum and maximum velocity of sewage. Next, we will discuss about the empirical formulas which are used for the design of shiver. The first formula is finding out mean velocity by Chessy's formula. So as per Chessy's formula, V equals to C into root over of Mi. Here V is the mean velocity in meter per second, C is the Chessy's constant, M is the hydraulic mean depth in meter, and I is the hydraulic gradient or longitudinal slope. This hydraulic mean depth can be found out by dividing area of the shiver with the wetted perimeter. So P is the wetted perimeter, and wetted perimeter is the section of the shiver or perimeter of the portion of the shiver which is coming in direct contact with the fluid. So here A is the area of the shiver. So this Chessy's constant C can be obtained by two different formulas. One is Bézin's formula, second one is Cutter's formula. So the Bézin's formula for finding out the value of C is equal to 157.6 divided by 1.81 plus K by root over of M. So here C C is the Chassis constant and M is the hydraulic mean depth. And K is the Bassin's constant. So this is the new constant, that is Bassin's constant. And this Bassin's constant, the value of K is different for different types of surface, such as for very smooth surface, the value of K is 0.109. For brick and concrete surface, the value is 0.290, and for rubble masonry surface, the value of K is 0.833. Then the next formula is Cutter's formula. So as per Cutter's formula, C equals to 23 plus 0.00155 divided by I plus 1 by N whole divided by 1 plus 23 plus 0.00155 divided by I whole into N by N divided by root over of M. So here also C stands for Chassis constant, M is the hydraulic mean depth, I is the hydraulic gradient, and N is the new factor which is known as roughness coefficient or rugosity factor or Cutter's constant. This is known as rugosity factor or roughness coefficient or Cutter's constant. So there are also different values of this N for different types of surface. So next we will move to the next formula for finding out mean velocity, that is by Mannin's formula. So by Mannin's formula, V equals to 1 by N into M to the power 2 by 3 into I to the power 1 by 2. So here also M is the hydraulic mean depth, I is the hydraulic gradient, and N is here also the rugosity factor. So for smooth surface, the value of N is 0.010. For concrete, it is 0.012. For stoneware pipe, it is 0.013. For brick or stone masonry, it is 0.017. For earthen channel, it is 0.025. Next formula for finding out mean velocity is by crimp and bruise formula. So by this, the mean velocity is equal to 83.50 into M to the power 2 by 3 into I to the power 1 by 2. So these are different formulas for finding out the mean velocity of flow of sewage. So now let us solve one problem. So the question is, calculate the velocity of flow and the discharge through a shiver of diameter 1 meter laid at a gradient of 1 in 500, and assume that the shiver is running full, and use Mannin's formula with N equals to 0.012. So as you know, the Manning's formula is 1 by n into m to the power 2 by 3 into I to the power 1 by 2. And here also the value of rugosity factor n is given as 0.012 and gradient is given as 1 in 500. See here, gradient is 1 in 500 and diameter is 1 meter. So see here, this is the diameter is 1 meter. So area will be equal to pi d square by 4. And then in order to find out this m, hydraulic mean depth, we have to divide the area of the shiver with the wetted perimeter. So this wetted perimeter is the portion of the shiver which is coming in direct contact with the liquid or the flow of sewage. So here it is, the condition is the shiver is running full. The condition is shiver is running full. That means the entire part is coming in contact. So the wetted perimeter will be equal to the perimeter of the shiver, that is pi d. So m will be equal to, area is pi d square by 4 into 1 by pi d. So pi cancel out, dt cancel out. So this will be equal to d by 4. So m will be equal to d by 4. So here d is 1 by 4. So the value is 0.25 meter. Okay. Then now we have all the datas with us. Then we will put the values in the formula. So 1 by n 0.012, in place of m put 0.25, in place of I put 1 by 500. So the velocity is coming out to be 1.479 meter per second. Then the question is, find out also the discharge through the shiver. So discharge is equal to area into velocity. So area is pi by 4 d square, velocity is 1.479, just we have found out. So by multiplying these two values, you will get the discharge as 1.16 cubic meter per second. So this is all about for today's class. In the next class, we will solve one more example. Thank you.